Good afternoon, students. So yesterday we have seen the homomorphism. No, 60th unit we have started. In that I have told the theorems. We have seen the definition of homomorphism. So today we'll see the fundamental theorem of homomorphism. So it is very important. So it will this theorem you will get for 10 marks question. That is the 10th B question. You will have this one. So if you'll see the statement of the fundamental theorem of homomorphism. So question will be state and prove the fundamental theorem of homomorphism. Okay. So it is 6.3.1 fundamental theorem of homomorphism. Let G and G dash be two groups and F is mapping from G to G dash be a homomorphism. Then G by that is kernel of F. This is kernel of F equals to image of F. Okay. So you have two statements for this theorem. So one is this statement, another one is every homomorphic image of a group G is isomorphic to some quotient group of G. Okay. Anything you can write as a statement for this one? Okay. So first one is let G and G dash be groups and G is mapping from G to G dash be a homomorphism. Then G by kernel F equals to that is equivalence to the whatever the symbol is there, that is called as isomorphism. Okay. G by kernel F is isomorphic to image of F. Okay. In particular, if F is an epimorphism, then G by kernel F is isomorphic to G dash. Okay, that you have to prove. Or else, if you write any one statement, it is enough. So every homomorphic image of a G is isomorphic to some quotient group of G. Okay. So for this, first we have to, we know that isomorphism means we have to prove that it is 1, 1 and on 2 and even it is homomorphism. Okay. We have to prove these three conditions. And also we have to define any one mapping such that we have to show that it is a well-defined one, that mapping is well-defined, and also it is 1, 1, and also it is on 2, and it is also homomorphism. If these four conditions are satisfied, then we say that whatever the homomorphic image of a group G is there, it is isomorphic to some coefficient group of G. Okay. So proof is first, let F be a homomorphism of G onto G dash and kernel F denote its kernel. We know that we have seen the definition of the kernel F. Okay. We have proved that kernel F is a normal subgroup of G and hence we can have the quotient group G by kernel F. Okay. Even we have seen the theorem that kernel F is a normal subgroup. Okay. First we have proven that it is a subgroup. Then we have proved that it is a normal subgroup. Okay. So also image F is a group of G dash. Okay. Even this theorem also is there. Image F is a group of G dash and hence we can treat image F as a image F as a image F as a group on its own. Okay. So for convenience, let us write kernel F. We are writing in shortcut as K. We have hence image F. Image F definition also we have seen. That is image F is equals to F of A such that A belongs to G, and kernel F is equals to A belongs to G such that F of A equals to identity element, that is E dash, where E dash is the identity element in G dash and in that is image F2. So in even in image F and also in kernel F, both the identity element is E dash. Okay. So after writing these all conditions, whatever we have seen in the previous theorems, now we are defining a mapping in which we are using that phi is there. Phi equal, that is phi is mapping from G by K to G dash. Okay, G by K is the here quotient group. It is mapping from G by K to G dash by, and we are defining the function as like this. That is pi of K into X is equals to F of X. Okay, in solving the theorem, we will use this function. For any Kx belongs to, for any Kx belongs to G by K. Okay, whatever the Kx is there for pi, it belongs to the quotient group with X belongs to G. Okay, first note that pi is a well-defined. Okay, we have to show that first pi is well-defined for, we have for any X comma Y belongs to G. So we are taking two elements, X and Y, they belongs to G, such that we are taking here the elements, that is xk equals to yk. Okay, first we are taking that xk is equals to yk, implies x inverse y belongs to k, where k equals to, we know it is a kernel of f. Okay, so f of, so we are taking here function, that is kernel f definition is what, f of x equals to e dash, no? So here in place of a, we are taking it as x inverse y. So therefore f of x inverse y equals to e dash. So when you're splitting this one, so you can write it as f of x inverse f of y is equals to e dash. Okay. So whenever it is equals to the identity element, and here inverse is there, f of x inverse is there. So when you take this f of x that side, on right hand side, what will happen? F of x equals to f of y will get. Okay, so therefore pi is whatever the function we have defined, that is a well-defined function. Okay, first this we have to show this one. Also for, we have to show that it is a homomorphism. Okay, for homomorphism we know that that is a f of a star b is equals to f of a, that is a circle into f of b. Two operations will be there here, one star operation and also one circle operation will be there. Okay, so the two operations, with the help of that we will prove the homomorphism definition. So here pi of xk into yk is equals to pi of, so whatever xy is there, you are doing the product of that one, that is x into y into k. Okay, so here whatever you are taking the two xk and yk, these are called as the product of two right cosets. We have seen the theorem in cosets. Okay, product of two right cosets equals to, that is pi of xy into k. So it is equals to f of xy, f of xy equals to f of x into f of y. Okay, so f of x value, so f of x is defined as, before we have defined, now it is a pi value. So that is pi of xk. So you are writing in place of f of x, pi of xk, and also in place of f of y, we are writing pi of y into k. Okay, this one. So therefore, this is whatever f of xy is there, that you are defining in the form of the homomorphism. Therefore, pi is a homomorphism. Okay, first we have proven it is a well-defined function. Next, we have proven it is a, that is a homomorphism. Since any element z in image of f is of the form, so to prove that it is a surjection, that means it is onto function, we are proving that since any element z in if, so image of f, you are taking any element z, it is in the form of z is equals to f of a. So f of a means what is the function there we have taken? So we have defined the function, no? Okay, we have defined the function, that is pi of xk is equals to f of x. Okay, in place of x we are writing f of a. So what will happen here? This is pi of ak will write. Okay, so that only we are defining here. So ak, whatever ak is there, it belongs to the quotient group g by k. It follows that pi is a surjection. That means we are showing that it is a onto function. Okay, so when we have shown the onto function, next thing is we have to show that it is a injection, that is 1 to 1. We know that injection means 1 to 1, surjection means onto. Okay, So for one-to-one function, we have to take f of x1 equals to f of x2. And we have to prove that x1 equals to x2. So then we can tell that it is the function is one-to-one function. Okay. For any x comma y belongs to G, pi of xk equals to pi of yk. Okay. We are taking two elements here, x and y. So we are equating them. Okay. So this whatever pi of xk is there, this pi of xk is f of x and this pi of yk is f of y. Okay. So f of x, we can write it as f of x inverse of y. Okay. So you're defining it as, that is f of x inverse y. So we know that from the above one here, this one, f of x equals to f of y. No, so in place of y, we are writing f of x. So f of x inverse f of x. So x into x inverse means we know it is the identity element. So it is equals to e dash. So x inverse y belongs to kernel f equals to k. So we got here e dash. Whenever we'll get function of f of x equals to e dash, we know that it is the definition of the curl f. So x inverse y belongs to curl f equals to k, implies that is xk equals to yk. So whatever the elements you are taking here, xk and yk, you are getting that elements as xk equals to yk. So it is an injection. Okay. Thus pi is an isomorphism of G by K onto image of F, and hence G by K is isomorphic to image of F. Okay. So if F is an epimorphism, then image of F is equals to, that is G dash, and hence G by K quotient group is isomorphic to G dash. Okay. So like this, we have to prove that the fundamental theorem of homomorphism. Okay. So first thing is you have to define one function. The function will be, it is a pi will be there. So that pi function, you have to define that one, that is pi of f of x equals to, or pi k of x equals to f of x. Okay. Through that function only, you have to show all the conditions. So first condition is, it is a well-defined function, that whatever function is there, that function is a well-defined function you have to show. And second thing, you have to show that it is a homomorphism. And third thing is, you have to show it is a onto function. And fourth one is, you have to show that it is one-to-one function. Okay. If you show these all conditions, then we can say that it is isomorphic to G dash. Okay. So this is the important one. So try to practice this theorem. So after this, so 6.4 is we have permutation group is there. So permutation group, on this you have Cayley's theorem is there, which is very important. So sometimes this theorem is also asked in the examination for 10 marks question. So if you are not getting the fundamental theorem of homomorphism, then this question will be asked for 10 marks question. So before that, we have to know the definition of what is a permutation group. Okay. So you can see the introduction here. And after that, we have the definition here. That is, let S be a finite set with n distinct elements. Okay. So you have one finite set, we denote with S. It has n distinct elements, means different elements. Then a 1-1 mapping of S onto itself is called a permutation of degree n. Okay. So we call it as a permutation of degree n if the function, or if whatever the mapping you are telling, if that mapping is, you can take like this, F, S to S onto itself, no? So S to S, if it is 1-1 and also onto. Okay. If a function, if we have a mapping, F is a function which is mapping from S to S, where S is a finite set with distinct n distinct elements. So if the mapping is 1, 1 and onto, we call it as a permutation group of degree n. Okay. So why we are taking here permutation definition? Because in Cayley's theorem, we have the permutation is there. Okay. So there, if you know the definition, you can tell this one. Okay. So next, Cayley's theorem is there. It is 6.4.2. So this theorem, sometimes statement will be given and you have to do the only proof, but almost compulsory it will be given state and prove the Cayley's theorem. Okay, in rare case you will get the statement. Okay, so Cayley's theorem statement is every finite group is isomorphic to a group of permutations on some set X. Okay, every finite group is isomorphic to a group of, here also whatever the finite group is there, it is isomorphic. Isomorphic means what you have to show? It is a well-defined function. It is onto function. It is one-to-one function. It is a homomorphism. Okay, these 4 conditions you have to show if it is isomorphic. Then to a group of permutations on some set X. So here we are taking the set as X. So permutation means you have to show the condition of 1, 1 and also onto. So here we have to show 6 conditions here, okay, with respect to of isomorphism and with respect to of permutations. So for this proof, let G comma dot, here dot is the operation we are taking, be a group, take the set G as X. Okay, whatever the set G is there, you take that as X, okay, capital X. For each A belongs to G, let us define a mapping f of A of X, okay. Wherever X is there, it means it is the set G only, into X by f of A of X equals to AX, okay, function f of AX equals to AX, okay, this is important, this definition. So the product AX of A and X in the group G for all X belongs to X, okay. So this is the important one, you have to remember this one, okay. Now we are showing that it is a permutation group, means first thing you have to show 1, 1 and next one is you have to show that it is onto, okay. So first 1, 1 means then for any X comma Y belongs to capital X, FA of X equals to FA of Y, okay. So normally in other problems like this, we'll take f of x1 equals to f of x2 and we'll show that x1 equals to x2 for one-to-one function. Here also we are defining in the same way, f of x equals to f of y implies what is f of x? It is defined as ax and ay. On cancellation law, this a and this both, a on both sides will get cancelled. You will get x equals to y. Okay. So we got that one-to-one function is satisfied. Okay. Hence, f of a is an injection. That means one-to-one function. Next thing is we have to show that it is onto function. So for onto, we are defining also for any y belongs to k, we have, that means for onto function, we need A inverse of y. So A inverse of y belongs to k. So this A inverse is the element in G. Okay, whatever A inverse is there, this A inverse is also element in G. Okay. So now we are combining this A inverse and also this Y. So this is equals to X. No, G means we are taking it as capital X. So therefore A inverse Y belongs to X, and we know that we are substituting in the function whatever it is there. So f of A in place of X, we are writing A inverse Y is equals to A into, this is in place of X. In place of X, what you are writing? A inverse Y. Okay. So this A and A inverse, if you'll take outside and Y. So what will happen? A into A inverse value is E. So E into Y, identity element into Y is equals to Y. So this condition of onto function is satisfied. Okay. So here you can write A belongs to G implies A inverse belongs to G. So where G is, we know that it is equals to capital X. So for the definition of onto function, we are taking A inverse. Here we are taking Y belongs to X, no? So in place of X, this A inverse Y we are substituting. Okay. So remember that one. So now 1-to-1 function is satisfied and also onto function is satisfied. Therefore, what the function we have defined here? This is the function, no? That is, therefore, if A is a surjection we have shown. After that, thus, if A is a Thus, FA is a permutation on X. Okay. The conditions of permutation are satisfied here. Okay. So, FA belongs to SX for each A belongs to G. Okay. Now, we have to show that it is isomorphic. To show that it is isomorphic, we need to show the conditions are there. Whatever the conditions are there, for that you are defining pi here. Whatever phi is there, it is mapping from G to S of X by, this is important. Okay, we are defining phi of A equals to F of A for all A belongs to G. Okay, we shall prove that pi is monomorphism, that is injective homomorphism for any A comma belongs to same condition we have to show. Okay, so here first it is homomorphism we are showing. Okay, for any A comma B belongs to G, we have homomorphism means what? You have to remember this. F of A star B is equals to F of A circle F of B. Okay. This is the condition for homomorphism. Okay. So we are defining F of AB. Function is there, no, of X equals to, what is there? There is AB into X. Whatever here AB is there, that AB into X. By associative property, you can take A outside and BX. Okay. Now, this AB into X is equals to A into BX. Okay. A into BX means this whatever is there, it is in the form of F of A into F of B of X. Okay. F of B of X means what we'll write? We'll write it as BX. Okay. This BX is F of BX and whole F of, if you take this as X, this whole part is this one. Okay. So now you are taking F of B outside. What will happen? F of A circle F of B of X. Okay. Okay. Like this, we can prove this one. If you want, whatever the homomorphism is there, you can do in simple form also. If you want, just I will tell that one. Simple form is that if you have any confusion here, so to show pi is, okay, pi is homo means let A comma B, A comma B belongs to G, implies we know AB belongs to G. Okay. So pi of AB is equals to F of AB you take. Then F of AB. So F of small a and F of small b is equals to, we know that it is pi of A, pi of B. Okay. So therefore, you can tell that pi of AB is equals to pi of A, pi of B. Okay. Simple way you can show that it is a homomorphism. Okay. Homomorphism definition is F of A star B is equals to F of A circle F of B. Okay. So here let A comma B belongs to G, A into B belongs to G, pi of AB is equals to F of AB. So F of A into F of B means we are write it as pi of A into pi of B. Therefore, this is equals to this one. So you can do like this or whatever in the textbook it is given, no? that you can do. So there also, it is from the definition only. Okay. So now we have shown that it is homomorphism. Okay. So here also it is given, see, f of AB is equals to f of AB equals to f of A circle f of B. That is pi of AB is equals to pi of A circle pi of B. Okay. This proves that pi is a homomorphism. Now we have to show that it is 1, 1. So for showing 1, 1, we are taking for any A comma B belongs to G, pi of A equals to pi of B. Okay. So what is the function we have defined? Pi value we have defined as f of A, and pi B means f of B we are writing. If you take for this one function, that is f of A of x equals to f of B of x for all x belongs to x. Okay. F of Ax means this one above we have defined no for permutation group. That is f of Ax equals to Ax. Okay. From that we are writing here f of Ax equals to Ax, f of Bx equals to Bx. So this actually this is not there. So when you do the that is the cancellation on a x on both sides, if we take out this x on both sides, what will happen? A equals to B you will get. So then we can show that it is a onto one, that is a 1-to-1 function. Okay. So same condition we are defining here. Next, what we have to show, it is a surjection. That means we have to show that it is onto function. Therefore, pi is in an injection and hence pi is an monomorphism. Okay. We know that monomorphism means if it is a 1-to-1 function, it is a monomorphism. Now we know that image of pi is defined as pi of A such that A belongs to G. We know pi of A is defined as f of A such that A belongs to G. Okay. And image of pi is a subgroup. Image of a image image of pi is a subgroup of S of x. Also can be viewed an isomorphism of G onto image of F. Thus, G is isomorphic to a subgroup of F of x, S of x. Okay. Or else, directly if you want to show that pi is onto, you can write like this. Pi is onto, if you want to show, for Fa belongs to G dash, that is, this is codomain. We know that what is codomain and domain. Okay. There exist A belongs to G. There exists A belongs to G. This A is in the domain we have. Okay. Such that pi of A is equals to f of A. Okay. Then we can tell that pi is onto. Okay. So if you want, you can write like this also for onto definition. That is to prove that a pi is onto. Okay. So that is pi is onto means for FA, whatever the function FA we have defined, if it belongs to G dash codomain, there exists A belongs to G domain such that pi A equals to FA. Okay. Pi A equals to FA. Therefore, pi is onto. Okay. So all the conditions are satisfied. Therefore, thus G is isomorphic to subgroup of Sx. Okay. Okay, this theorem is also completed. Next, in this 6.5, we have what is a permutation groups, the symmetric groups. Symmetric groups are we represent with SN, and we have the permutation groups are there. The symmetric groups. Okay. So here symmetric group we denote with SN. First we have seen the definition of what is a permutation. No, just now we have seen that is a permutation means it is a function from S to S, a permutation of a finite set. S is bijection, that is 1 and on 2 means bijection only, no? Then we call it as a permutation group. Okay. So if S equals to only one single element, we'll write the permutation as, we know that. So permutation, this one, okay, you can see, we'll write the function like this. Function F is equals to 1, 2, 3, n distinct elements. For that, you will have the images F of 1, F of 2, F of 3, F of n. Okay. For example, if you take F equals to 1, 2, 3, 4, 5, you have the images 2, 4, 3, 5, 1. Then F belongs to S5. Okay. Why? Because in this 5 elements are there, no? We know that F of 1, whatever the images are there, that you are writing as like this. Okay. So if any set is there like this, S equals to 1, then we tell that it is the identity element, means it is having only one mapping. That is, if you take like this mapping, so one element is mapping to one only. Okay. So if you have two elements, if S equals to, that is 1, 2 we have. So what will happen? You have the two chances of getting the mapping. That is 1, 2, 1, 2 we have. So 1 may be mapping to 1, 2 may be mapping to 2. This is called identity mapping. So this is one possibility. Another possibility is 1, 2 if you have 1, 2. So like this you can do. 1 is mapping to 2, 2 is mapping to 1. Then we can write the permutation as like this. Permutation P is equals to 1, 2, 1, 2. Okay. From this mapping, we are writing 1, 2, 1, 2. Another permutation is you can write 1 is mapping to 2, 2 is mapping to 1. Okay. So like this, we can write the permutations here. By having the images, we can, whatever the first row is there, it is the elements we are taking. And what are the images we are getting, that you write as a second row. Okay. So in this, we have different definitions are there. So you have already in intermediate, you have the concept of permutations we have. Permutations and combinations is there, no? Okay, here we have seen. Definition is there. So after this, equality of two permutations means if whatever F and G be two permutation, then they are called if and only if F of A equals to G of A. Next we have F is called a cycle of length. Okay. So first, if you know identity, we have the concept, no? Identity permutation means we'll represent with like this. Identity permutation means I equals to 1, 2, 3. If you have the mapping with the same elements. Okay. So cycle. Okay. Cycle permutation or cycles. Whatever the cycle we are writing for the permutation, that is, if you have any permutation like this, 1, 2, 3, 4, 2, 3, 4, 1. Okay. So for this, you can write the cycle as, that is, we have to see the mapping. 1 is mapping to 2, 2 is mapping to 3, 3 is mapping to 4, again 4 is mapping to 1. Okay. We are writing this, permutation as cycle. In this form, if you write, this is called as a cycle permutation. Okay. So how you got this one? This is 1 is mapping to 2. After that, 2 is mapping to 3, 3 is mapping to 4, 4 is mapping to 1. If you write like this is called as a cycle. Okay. Okay. Whenever we'll have the cycle of length 2, we call it as a transposition. Okay, this is the important one. A cycle of length 2 is called a transposition. Means like this 1 2 or 2 3 or 3 4, like this. Whatever you are getting the cycles of length. Length means the number of elements present in the cycle. Okay, that is called as the length of the permutation. Okay, so this is called as transposition we have here. So this check your progress you have here. For f comma g belongs to S8 given below, compute f circle g and also g circle f and f inverse. Okay, so this is the product of the two permutations. Product, or we call it as a composition of two permutations. So we'll write f circle g and also g circle f. Okay, you know that f circle g means F circle G means first you have to take this permutation G. Okay. Whatever the elements are there in this, you have to take that permutation G, and with respect to of G, you have to compare the elements of F. Okay. So first above you write this one same. That is 1, 2, 3, 4, 5, 6, 7, 8. Okay. This first row, whatever it is there, it is you write in the order. Okay. So now F circle G means 1 is mapping to 7. Okay. 1 is mapping to 7. Here 7 is mapping to what? 8. So here you have to write 8. Next 2 is mapping to 2. Next 2 is mapping to 5. So here 5. Okay. Next we have 3 is mapping to 4. 4 is mapping to 2. Okay. 4 is mapping to 6. 6 is mapping to 6. Next, 5 is mapping to 5. 5 is mapping to 1. Next, 6 is mapping to 1. 1 is mapping to 3. Next, 7 is mapping to 8. 8 is mapping to 7. 8 is mapping to 3. 3 is mapping to 4. So, if you see in the denominator also, we got 1, 2, 3, 4, 5, 6, 7, 8. So whatever we have done, that is the correct product of the two permutations. Okay. You have to first you have to compare the G permutation. Then you have to compare the F permutation for F circle G. If it is a G circle F, okay. If it is a G circle F means numerator, that is the first row, you write same one, 5, 6, 7, 8. Okay. So first you have to compare F, then you have to compare here. First you have to compare F and then you have to compare G for G circle F. So 1 is mapping to 3, 3 is mapping to 4. Next, 2 is mapping to 5, 5 is mapping to 5. 3 is mapping to 4, 4 is mapping to 6. 4 is mapping to 2, 2 is mapping to 2. 5 is mapping to 1, 1 is mapping to 3. 6 is mapping to 6, 6 is mapping to 1. 7 is mapping to 8, 8 is mapping to. Here we have taken the so these two we have done now. Okay. So here what happened? 4 is mapping to 2. First F no. 4 is mapping to 2. 2 is mapping to 2. Okay. 5 is mapping to 1, 1 is mapping to 7. Okay. 6 is mapping to 6, 6 is mapping to 1. Next, 7 is mapping to 8, 8 is mapping to 3. Next, 8 is mapping to 7, 7 is mapping to 8. Okay. So this is the G circle F, that is 4, 5, 6, 2, 7, 1, 3, 8. Okay. So like this, we have to find F circle G and also G circle F. F inverse means it is the inverse permutation. Inverse permutation is nothing but whatever the second row is there, that you have to write as the first row. Then we call that it is a inverse. So he is in the question he has asked for the F inverse. So F inverse means first you write like this, F inverse equals to first interchange of this one, no, that is 3, 5, 4, 2, 1, 6, 8, 7. In the denominator, that is the second row, it is a 3, 4, 5, 6, 7, 8. Okay. So interchange of the second row to first row is called as a F inverse. So we got like this. So if you want to write this in the order, then we have to write like this. So first you write 1, 2, 3, 4, 5, 6, 7, 8. Okay. So then, so here 1, what it is mapping? It is mapping with 5. So right here 5. 2, it is mapping with 4. Next 3, it is mapping with 1. Next 4, it is mapping with 3. Next 5, 5 it is mapping to 2. Next 6, it is mapping to 6. 7 is mapping to 8. 8 is mapping to 7. Okay. Now we got it. Now we have written it in the order. That is, we got 5, 4, 1, 3, 2, 6, 8, 7. So like this, we have to write the F inverse or G inverse or anything. First you interchange that one, then you write in the order. Okay. So second problem is that your F value and G value in cycle it is given. So that cycle you have to write in the form of the permutation, and then you have to find F circle G and also G circle F and also F inverse. Okay. So it is given as a 3125 F values. So here the permutation we given in the question is S8, no? Okay, so we can write this F equals to 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now here 3 is mapping to 1, 1 is mapping to 2. Okay, here you will get 2. 2 is mapping to 5. 3 is mapping to 1. So here 1. So 4 is not there. Whenever it is not mentioned in the cycle means it is identical. Okay. 5 is mapping to 3. 6 is not there. So 6, 7, 8. These are all identical. Identity permutations we have. Okay. So we got this as 2, 5, 1, 4, 3, 6, 7, 8. When you'll take G, G is equals to 1, 2, 3, 4, 5, 6, 7, 8. Okay. So G is 1 is mapping to 8. 2 is mapping to 6. 3 is not there. Means it is the identity. 4 is mapping to 2. 4 is mapping to 2. 5 is mapping to 4. 6 is mapping to 1. 7 is not there. So 7 is identical. 8 is mapping to 5. Okay. So if you find F circle G, F circle G means we have to compare first G. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So G 1 to 8, 8 to 8. Next 2, 2 to 6, 6 to 6. Next 3 to 3, 3 to 1, 4 to 2, 2 to 5, 5 to 4, 4 to 4, 6 to 1, 1 to 2, 7 to 7, there also 7 to 7 only, 8 to 5, 5 to 3. So we got this as 86154273. Okay. So like this, we have to find whenever cycle are given, cycle, you have to convert that cycle into permutation, and then you have to write F circle G and G circle F and also F inverse. Okay. So whenever this cycle is there like this, for this also we can write F inverse. F inverse is equals to 5213 like this. Okay. So just if you interchange the elements, then we can tell it is the inverse of the permutation. Okay. So next third one, you can try by your own. That cycle you convert into permutation and then you do the F circle G and G circle F. So after this problem, okay, here definition of disjoint cycle we have. Okay. Two cycles, F equals to A1, A2 up to AR, and G is equals to B1, B2 up to S. In SN are called disjoint if A1, A2 up till AR and B1, B2, BS are disjoint. That is, if they have no common elements. Okay, if two cycles, if they don't have common elements, then they are called as the disjoint cycles. Okay. So whatever the problems we have done, so for that problems, he will ask to write that problem in the form of transposition and also in the form of disjoint cycles. Okay. Determine the cycle decomposition of the following permutation in S9. Okay, S9 here up to 9 elements are there. Here permutation is given. So we have to determine the cycle with decomposition of the following permutations. And even the question will be asked like this also. Write in the disjoint cycles. So for that solution is given. You can see that here express the following permutations as a products of disjoint cycles and as a product of transpositions. Okay. 11th one. Express the following permutations as a product of disjoint cycles and as a product of transpositions he is asking. So whatever the permutation is given, that you can write as a product of disjoint cycles. So first you write it as that is 1 is mapping to 3 is mapping to 1. So close here, circle. Next 2 is identical, so no need of writing the 2. Okay. Next 3 is completed, 4 is there, 4 is mapping to 5 is mapping to 7 is mapping to again 4. So you close here. So next circle, 6 is there, 6 is mapping to 8 and 8 is mapping to 6. So here also we have to close that. Why? Because it is stopped. The mapping is stopping here. Okay. So 1, 2 is the identical. 3 we got 4, 5, 6, 7, 8. Okay. So these are the disjoint cycle. Disjoint means no two cycles should have the common elements. So in this 1, 3 is there. In here 4, 5, 7 and here we have 6, 8. Okay. That means here we have no common elements in these cycles. Okay. And as a products of transpositions means cycle of length 2. Cycle of length 2 means already 1, 3. The length is 2. For this one, you can write as transposition. First one is 1, 3. Next circle. 4, 5, we can write it as 4, 7, and circle 4, 5. And third one already it is in single only, that is a length 2 only. So it is 6, 8. Like this is these are the transpositions. Okay. And these are the disjoint cycles. Disjoint cycles you have to write like this, and transpositions you have to write like this. Second one you can try by your own. So they are in the form of that is a disjoint cycles are there. So you have to write them in the form of the transposition, and then you have to find the product of transposition and also disjoint cycles. Next we have the that is a topic about the in permutation groups. The alternating group is there. So alternating the group is denoted as like this AN. Okay. Symmetric group means it is denoted as, we have seen no before, one symmetric group means it is SN. Okay. Alternating group means AN. So this is the definition we have. For this theorem is there, that is let a permutation F in Sn be represented as F and these. Okay, but theorem is not important. Just the definition of alternating group is just you have to know that one. Here we have the, before that, so before that we have the concept of what is even permutation and also what are odd permutations. A permutation in Sn is called as even permutation if it is a product of even number of transpositions. Okay. So if it has even number of transposition, then it is called even transposition. A permutation is called odd permutation if the product have odd number of permutations. Okay. Odd number of permutation, you know. Okay. So here you can take an example of even permutation is that if you have the elements like this 1, 2, 3, 4, 5. Okay. Even we have the that is the order of the permutation will be there. That is the order of permutation is equals to number of elements present in this one permutation. Okay. 1, 2, 3, 4, 5. We have 5 elements here. So you have to write them as a product of transposition. No? So S equals to, that is 1, 5. We can write 1, 4, 1, 3. Next to 1, 2. So how many we got? 1, 2, 3, 4. Here we got 4 transpositions. That is, it is a even transposition. So 1, 2, 3, 4. So these are the 4 transpositions. So it is a even transposition. So if we have here 4 even number of elements in the set, then we'll get odd transpositions. Okay. So you can take S equals to 1, 2, 3, 4 are there. Okay. Here order of S is equals to 4 we have. So number of permutations equals to 1, 4, 1, 3, 1, 2. So how many we got? Number equals to 3. So it is a odd permutation. Okay. So like this, you can, on the number of transposition, we can represent what is even permutation, what is odd permutation. You can determine whether the following permutation or even or odd. In check your progress, it is given. Okay, you can see an R cycle A1, A2 up till AR. So F equals to in disjoint cycles it is given. So you have to write them in the permutations and you have to check that whether they are odd or even permutations. Okay. Next, we have one important theorem in this. It is the that is let n is greater than 1, the set an let n is greater than 1, the set an of all even permutations in Sn is a normal subgroup of index 2 in S, and that is mod of an is equals to n factorial by 2. Okay, this is the most important one. Sometimes it is asked for 10 marks also. So you can just go through this theorem, whatever proof is there that you can see. And here alternating group of degree n definition is there. Okay, 6.6.4. Okay, the subgroup an of all even permutation in Sn is called the alternating group of degree n. If n is greater than 1, then mod of an is equals to 1 by 2 n factorial. So this is the definition of alternating group. So after that, you have worked out exercises are there. These are the important topics in 6th unit. Okay. So by this, we are completing the block 2. So I hope so. This is the last class, or actually 2 more classes should be there. But up till now, we didn't got any schedule. So if it is the last class, by this, we are completing the block 2. So two blocks are there. It is a rings we have. Okay. Rings one. Third block is about the rings. So first block and second block, all the important questions I have told while going through the whatever the topics we have covered, I have told all the important one. So here, if you see the rings 1 and rings 2, it is a block 3 and block 4. So even in the introduction class, some important questions I have told. Just we will go through the 7th one, that is the rings we have. Rings definition is there. That is 139 page number. You have the what is a finite ring we called 7.2.3. And we have the definition of what is commutative ring, what is a zero ring, and what is a null ring. We have definitions. Okay, page number 150, 7.3.9. This is the important theorem. If R is a ring, then prove that center R is a subring of R comma plus comma dot. Next, 153 page number 7.4.1. We have problem this one. Next, 154 page number 7.4.2. Okay. And one more important is 156 page number, it is 7.4.5. And 157 page number 7.4.7. This is the 5 marks question you will get. And check your progress 11th question, 158 page number. 158 page number only 7.4.9. This is the very important and regularly asked question. Okay. Next, if you'll see the unit 8. One 67 page number 8.3.5. Okay, every field is an integral domain, but the converse need not be true. Okay, this is the important one. Next, 168 page number 8.3.6. Every finite integral domain is a field. 837 sorry, 8.3.7 theorem and 8.3.8. Next we have characteristic is there. That is 172 page number 8.3.14. This is the 5 marks question you will get. 174 page number 8.4.2. Okay. This is the 10 marks question. 8.4.2. Next, if you see the 9th unit, 181 page number. Okay, 181 page number 9.2.8. The intersection of any two ideals of a ring R is again an ideal of R. Okay. So this is the regularly asked question. This is also important. 183 page number 9.2.10. If R is a commutative ring and A belongs to R, then I equals to, that is left and right ideals we have in this. 9.2.14 and 9.2.15. Every field is a integral principal ideal ring. Next, 193 page number 9.4.2. 194 page number 9.4.3. If you will go to the last block, we have homomorphism is there. That is 206 page number. The homomorphic image of a ring is a ring. Okay. 10.3.2. So in this also, you will have the fundamental theorem of homomorphism of rings will be there. Okay. There we have seen the groups. No, here rings will be there. That is also for 10 marks question you will get. That is 210 page number 10.3.6, 10.3.7, 10.3.8, 10.3.9. And page number 212, you have the fundamental theorem of homomorphism of rings. Okay. This is also important, 10.4.1. Next, if you see the 11th unit, 220 page number 11.2.5 and 11.2.7 and 11.3.8 page number 223, 11.3.8. Next, 225 page number 11.3.11. This page number 226, 11.3.12. This is the very important theorem you have chance of getting for the 20 marks question. Okay. Let F be a field and F of X be the ring of polynomials over F. Then F of X is an Euclidean domain and hence a principal ideal domain. You can see the proof for this one. It is a very lengthy one. So compulsory it will be asked for 20 marks question. Okay. Next, 230 page number 11.4.2, 11.4.3. Next, if you see the 12th unit, 12.2.3, every prime element is an integral domain is irreducible. The converse is not true in general. Okay. This is the 5 marks question you will get. And 12.2.5, 239 page number. And 241 page number, 12.3.2. This is also chance for getting the 20 marks question. Every Euclidean domain is a unique factorization domain. Every Euclidean domain is a unique factorization domain. So 20 marks, 2 questions I have told. 12.3.4. This is also very important one. Regularly asked question this one. 12.3.4. Okay, these are the important questions we have. So first two blocks, if you'll see the classes videos, then you can see the important questions there. And these are the two blocks, last three. There is a third and fourth block, important questions. Okay. If you have two more classes, we'll see in the next class. If classes are not there, okay, this is the last class. Okay.